Hello, my name is Jonathan Hoy, and today I will present to you my Autonomous Robotic Arm project. For this project, there were two main goals. The first goal was to design a robotic arm capable of autonomously picking up a small colored object. The second goal was to incorporate MATLAB and Arduino into a project. To achieve the first goal, visual feedback was utilized from a USB webcam. Second, multiple control loops were utilized within the arm. And finally, inverse kinematics were used to determine angular set points within the arm. Mathematically, the robotic arm can be modeled as three linkages. The challenge that is presented to us, however, is that given an x and y coordinate from our sensors, how do we determine the three corresponding angles of the robotic arm? In order to calculate these angles, we must first know the physical constraints acting on our arm. In this case, each link has its set length, and each link has a set angular restriction that it cannot go past. Using these restrictions, we can map out an XY planar region of application for the robotic arm. The region denoted in red is the area which the robotic arm can grab in. Outside of this region, however, the robotic arm cannot grab. Using the restrictions as seen from the previous slide, now we can solve the problem by using the optimization toolbox. The command used to solve this problem is fmin_con. The following equations below are minimized, and they are also subject to the following constraints. In order to ensure that the robotic arm control system functioned properly, it was of immense importance that the proper sensors were used for the job. In this case, sharp IR distance sensors were used to determine the radial distance between the arm and the object. A USB webcam was used to determine the color of the object and the angular orientation of the object in space. Accelerometers were used to provide feedback data on the robotic arm angles. And finally, a force sensor was used to determine if the robotic arm gripped the object or not. Of equal importance to the control system is proper actuator selection. In this case, 4 DC motors were used and one 180-degree rotation servo was used. In order to understand what the control system is doing, it is important to visually know where all the sensors are in your system and how they are contributing to the main goal of your robotic arm, which in this case is to pick up the target object. To properly determine the distance to the target object, we must mathematically determine the relationship between the two distance values given to us by our IR sensors and the x distance which we want. In order for the arm to be classified as autonomous, it had to be able to recognize the target object and determine the coordinates of where to pick it up. In order to achieve this, image recognition was utilized. In this case, an RGB image was taken of the target object and its surroundings. Then the image's red, green, and blue values were given threshold values such that the pixels that were not red or orange were filtered out. Using this new image as seen below, the centroid of the target was then determined and converted to angular errors to send to the servo motor. Seen below is a block diagram layout of the control system hardware used in the robotic arm. One thing to note here is that the MATLAB interface for Arduino allows the computer to run the master program in MATLAB, while the Arduino microcontroller follows the commands issued to it by MATLAB. Shown next is the flowchart of the master program ran in MATLAB by the computer. One clear benefit in running MATLAB is that it has extensive toolbox support in bringing together various coding tasks such as optimization, image acquisition, image processing, and data acquisition. Shown here is the completed robotic arm setup running on MATLAB. As you can see from this photograph, each piece of hardware used on the robot contributes to the overall task of autonomously picking up the target object. In this next slide, we will now see video feed of the robotic arm in action. The master program first starts out by having the arm in a default set position. The camera then takes pictures of its surroundings. Once the target object is located, MATLAB then creates angular set points for the links, and the control algorithms are executed until the target object is reached. The gripper then grabs onto the object, and it is then discarded off to the side. Thank you very much for your time, and I look forward to making more videos involving robotics and MATLAB in the near future. Goodbye.